Good morning. I would like to thank the organizers for this opportunity to present a synopsis of discussions that my colleague, Dr. Bob Bowden, and I have been having over the last 5 years around the consideration of ethical issues in the deployment of host plant resistance genes. I'm cognizant that there may be well-reasoned disagreement with the content of this presentation, so I begin with this disclaimer taken from Peter Singer in the introduction to his textbook, Practical Ethics. Learning from disagreement leads to a more defensible position and is one reason why, even if the views I hold are mistaken, they should be discussed. So what are plant breeding ethics? Generally speaking, ethics are moral principles that govern a person's behavior or the conduct of an activity, and applied ethics is the branch of ethics that has as its starting point practical normative challenges. It starts with the actual situational problem rather than with a philosophy. Plant breeders generally share 4 foundational applied ethical principles. First, a care for humanity, for feeding the 10 billion is the primary guiding ethic of the discipline. It is why we do this. The breeding community recognizes freedom from hunger and freedom from malnutrition as basic human rights. Increasingly, this ethic of care is coupled with an ethic of concern for environmental sustainability of agricultural production. Secondly, breeders adhere to an ethic of attribution, the right of the breeder to recognition for that which she has created. Coupled with the ethic of attribution is an ethic of access, that my fellow breeders have a right to be able to use my finished germplasm as parents in their breeding efforts. Finally, breeders generally recognize the need for a just return on the economic investment made in plant breeding, which is essential to support the ongoing investment in the activity of crop improvement. These last 3 ethics, when applied to finished varieties, have been captured in a regulatory system. The National Plant Variety Protection Systems and the International Convention for the Protection of New Varieties of Plants ensure attribution, access, and mechanisms for economic return. The raw materials of plant breeding, plant genetic resources, are regulated through another structure, however. Following ratification of the Convention on Biological Diversity in 1993, genetic resources are no longer managed as a common heritage, but as resources with sovereign rights. Genetic resources can no longer be accessed without prior informed consent and mutually agreed terms. The International Treaty on Plant Genetic Resources for Food and Agriculture and the associated multilateral system manage access to genetic resources on behalf of member nations. Now, I included this image of the migration routes of the yellow rust pathogen for context and contrast. While the human breeding enterprise has adopted mechanisms to regulate the distribution of genetic resources in finished cultivars, the rust pathogens migrate without regard to international borders or conventions. We face a global challenge. Everyone watching this presentation likely has their own story of the path to failure of once mighty host plant resistance genes. But rather than review the litany of disasters, I will focus on a path to disaster prevention through stewardship. The broad considerations for gene stewardship are that there's a cost to trait deployment, generally a 2-phase process from trait identification and germplasm distribution, followed by incorporation into elite germplasm, and the cost of ramp-up through seed distribution systems. Typically, there is a lag time between the demise of one resistance gene and the delivery of the next. The breeding enterprise tends to focus on genes that work until they don't. In this lag time, there's a cost to producers and consumers from lost yield or externalized costs for fungicide application. Finally, we have regarded host plant resistance genes as an infinite resource, assuming that we'll always be able to find a new resistance from some landrace or ancestral relative. But our collections of landraces and relatives are increasingly well characterized and have become finite. I would suggest we need to consider the very real possibility that we will exhaust the readily accessible genetic variation and increasingly be forced to mine more challenging genetic resources. If we must confront the prospect that our genetic resistance well is not infinitely deep, we must consider a new ethic for breeding. There are variant forms of a conservation ethic. The conservation ethic that I find most applicable to the breeding enterprise was articulated by Gifford Pinchot. He was the founder and first chief of the United States Forest Service in 1905. He worked with President Teddy Roosevelt to bring the forests on the public lands of the United States under centralized management. Significantly, a central tenet of his leadership was that decision-making for forest use should be science-based. Pinchot's principle is often quoted as the most good for the most people for the longest time. How would we implement a genetic utility conservation ethic in the diverse global enterprise of plant breeding? Individual persons or organizations could act unilaterally. I could incorporate restrictions to support stewardship in material transfer agreements for pre-release material, but these would be effective only until cultivars are released. I could act to ensure that my released cultivars are genetically structured to support the conservation of resistance traits. This would improve the composition of the crop in production, but would be effective only until my colleague uses the research exemption of the PVP to gain access to the germplasm for crossing. Finally, plant patents could be used to protect fully novel resistance traits, but much of what breeders now have access to is firmly planted in the public domain. While some of my individual actions may promote conservation of genetic utility, extension to collective action of the breeding community could have far greater impact. We can draw insights from the behavioral sciences to guide collective action toward a successful outcome. Gavrilets and Richardson conducted a series of us versus nature simulations to describe the evolution of norm internalization for collective action. Norm internalization evolved under conditions that favor cooperation, where individual and group selection works to increase benefits and decrease costs. The work of Eleanor Ostrom to characterize the underpinnings of collective action noted that the world contains many types of people, some more willing than others to initiate reciprocity to obtain the benefits of collective action. A central conclusion of a combination of laboratory experiments and field observation was that people can learn to self-organize effectively for the common good. The behavioral sciences provide guidance in constructing a framework for collective action toward gene stewardship. Key take-home messages from a long series of public good experiments and extensive field observations of self-organizing groups are that successful self-organizing groups develop from small groups with a propensity to cooperate, who establish clear group boundaries and membership criteria. These self-organized groups for common pool resource sharing are sustainable when they retain these clear boundaries for membership, have a strategy for equitable sharing of benefits, incorporate participatory rulemaking, have selected monitors and graduated sanctions, provide a low-cost arena for conflict resolution, and externally imposed rules tended to crowd out endogenous cooperative behavior. Other interesting and relevant take-home messages are that those who believe others will cooperate are more likely to cooperate themselves, and face-to-face communication promotes cooperation. To wrap up this discussion, practical gene stewardship is now practicable. The well-developed science of population genetics provides for science-based decision-making for stewardship. The tools of modern molecular breeding are enabling technologies. It is no longer necessary to perform test crosses or progeny tests. Marker selection for resistance traits can be incorporated into all marker-enabled breeding strategies for genetic gain. Finally, the scientific community has the capacity for self-organization for the common good. An example of this would be the 1977 Asilomar Conference on Recombinant DNA that led to voluntary guidelines for recombinant DNA technology that continue to be effective, participatory, evolving tools 40-plus years later. All this having been said, I will close with an image of my favorite yellow rust gene pyramid next to its mother, which has durable resistance, and I will say thank you for your attention.